inviting. Thank you very much for inviting me to give a talk in the seminar series. So I'll talk about some work on global community detection using individual-centered partial information networks. And this is joint work with Dr. Xiao Han and Dr. Xing Tong here in Marshall School of Business. So here's just a quick outline of my talk. So I'll first talk about what motivated us to think about the setup, and in particular, what we mean by a partial adjacency matrix. And because our algorithm is spectral based, next I'll present some theoretical results related to the main signal term of the partial adjacency matrix, including its eigenvalues and eigenvectors. And as a byproduct of our analysis, we're also going to propose a new centrality measure, which determines how important a person is within the whole network. And then I will talk about actual community detection on the concrete models, the stochastic block model and the degree corrected version. And finally, I'm going to present some results using simulated and real data. So I'm gonna turn my video off as well, just in case the internet is not very stable. Okay. So network modeling has been a very popular research topic in the recent decade as the amount of network structured data grows at a very fast pace. Now, the general idea is that for a complex system with interacting components, we're going to represent it using a graph containing nodes and edges. Now, inevitably, there are some simplifications involved in this abstraction, but it also means now we can apply many mathematical and statistical tools to analyze this object. And the type of networks we focus on in this talk is social networks, which study people and their relationships. And here's, many of you have seen this picture before. Here's the worldwide Facebook network where the nodes are the users and an edge connecting two users if they're friends. And we can see also densely connected pockets of users, mostly based on the geographic locations. So just to set up again, we have a graph with a set of nodes, and they represent n individuals. And the edges, for simplicity, we assume them to be binary and directed. And of course, in reality, these edges can be weighted, it can be directed. Just for a start, we consider the simple case first. Now, in the statistics community, the kind of problems we are interested in is that, first of all, we want to infer the community memberships, latent community memberships of these nodes. Now, in the simplest sense, the communities represent groups of people who are more tightly connected with each other than with the rest of the network. You know, these can be groups of people who graduated from the same high school, or they share common interest on Facebook, and so on. People also estimate something called subgraph counts. So we want to estimate the number of stars, the number of wheels, number of triangles in the network, and as they represent certain specific kind of connection patterns. People also estimate node covariates. You know, for example, I'm interested in the proportion of HIV positive subpopulation in the whole population. And that's an example of a node covariate. However, most of the current literature focus on either you assume you have access to the full network, so you get a global view of the network, or multiple subgraphs from the full network can be sampled, and from which you combine all the information and to infer, you know, it can be community memberships, can be subgraph counts, and other things. However, as an individual in the social network, we often have to make decisions based on our local view of the network alone. In other words, I don't get to see the whole of the full network, nor do I get to see, you know, multiple samples, subgraphs of the network. So the question is, as an individual, how much do I see, or how much do I understand about the connections in the full network? So in this stick figure, you know, in the first layer, I know my friends, right? These are people directly connected to me, and I get to see these edges. Now, I probably also know who are my friends' friends. And now for many of us, this is probably the extent of our local network knowledge. Any edges further away from me are not observed. So now I'm sure that in a real network, there are people who get to see further with their local view, extending further away from the center. But the key here is that if we take an individual as the center, it is reasonable to assume whether an edge, a connection, can be observed by that person depends on how far away it is from the center. In other words, it depends on the path length from the center. And this is what motivated us to think about the structure, what we call an individual-centered partial information network structure. So here's just a toy example, making it more concrete. So we have a network consisting of 6 individuals. So this is the panel, the leftmost panel. And let's say we take individual 1 as the person of interest. And here we're using L to denote the person's knowledge depth. That is, the person knows all paths of length up to L, starting from the center. So for example, when L is equal to 1, this is the rightmost panel, the person only gets to observe the edges directly connected to them. And when L is equal to 2, then compared to the full network, the only missing edge is between individual 5 and 6. Now this edge lies on the path of length 3. So under L equals 2, we're not going to observe this edge. When L is equal to 3, then we recover the full network. So given an individual as the center, we can characterize their partial or local network by knowledge depth, or which is essentially the path length. Now, in our work, we're going to focus on the case L equals 2. And this is because, L equals 1 just gives you 1 star, right, centered at individual 1, which is rather uninteresting. And the 6 degrees of separation phenomenon, which essentially says it only takes 6 steps to reach anyone in the network, means that if you take a moderately large L, you're already going to recover the full network. So that's not very interesting either. L equals 2 is a reasonable starting point for investigation. And L equals 3 is going to involve more complicated analysis. So we'll just do L equals 2 for now. And the question we want to ask is that, can we infer everyone's community membership? Right? Do we want to do global community detection based on just this one piece of partial network alone? Now, the structure of our partial network is related to some of the very popular sampling schemes in the network literature, also in the quantitative social science literature. This includes the egocentric sampling, snowball sampling, and respondent-driven sampling. So all of these sampling schemes work by first selecting some individuals as the seeds, and then ask them to recruit their neighbors in some way. In egocentric sampling, you're just looking at the ego network, which means you only look at the net node plus their neighbors and the connections between their neighbors. Now, snowball sampling and RDS do this in multiple waves. Now, in the first wave, I'm going to recruit my own neighbors. And in the second wave, you're going to ask the neighbors to recruit their neighbors, and it goes on. And in RDS, the recruitment of neighbors can also be probabilistic, and the samples are weighted in some way to adjust for bias and variance. The key conceptual difference between this line of work and ours is that we are interested in what one instance of the partial network can offer. And this allows us to take the view that now we can compare what kind of network structure is visible to every individual. And some other differences include RDS-based methods are often used to estimate node covariance. For example, that you want to estimate the proportion of HIV positive people in the population, right? Or you want to estimate the proportion of stray youth. It's used as a way to sample hard to reach subpopulations. But in our case, we are interested in estimating latent community structure. And lastly, there are cases where it will be very hard to perform multiple sampling. Right? It will be very hard to sample multiple subgraphs. And in a lot of these cases, asymptotically, you need the number of subgraphs to go to infinity. And there are cases when it's hard to perform this sort of sampling step multiple number of times. So we just want to see what we can do with one piece of this partial network. So back to the setup again. So recall that we have a graph with a collection of nodes and a collection of edges. Because the edges are binary and undirected, we can code this graph into a adjacency matrix. Right? It's an n by n binary symmetric adjacency a matrix, where the ij's entry equals 1 if I and j have an edge connecting them. Now we will use B to denote individual one's perceived adjacency matrix within the full network based on knowledge length knowledge depth L equals 2. Now, without loss of generality, we are always going to, in our analysis, we're always going to center around individual one. If I'm interested in a different individual, I can always permute the matrix and make that person, number that person as my node 1 instead. So this is without loss of generality. So the question is, how can we write down B given A? So let's go back to the toy example again with 6 individuals. So here is the original, the full adjacency matrix A encoding all the relationships. And now under L equals 2, I don't observe the edge between node 5 and 6. So these entries are 0 in the B matrix. So more generally, we have this relationship connecting the entries in B and the entries in the adjacency matrix A. And basically, an edge between node I and J is observed by node 1 if and only if at least one of the 2 nodes is a neighbor of node 1. Right, so going back to this toy example, the edge between 5 and 6 is not observed because neither 5 or 6 is a neighbor of 1. And the other, all of these other edges satisfy this constraint, so they are observed. And in matrix notation, we can write B in this form, right, where S is a diagonal matrix encoding the neighbors of A. Right, so so the ith diagonal of S is equal to 1 if the ith node is a neighbor of individual 1. And so roughly speaking, you have this term, counting edges with one end of the node pair being a neighbor of 1, and you have this term counting the other end of the edges being a neighbor of node 1, and then you account for double counting. So it's very much like calculating a union of 2 events. Now, let's do some analysis on this property of the B matrix, which looks different from the usual full adjacency matrix. Now, in order to derive some spectral properties, we will first impose this commonly used low rank assumption on the full matrix A. So we'll assume the expected value of A, the population version of A, in other words, has rank K. And the eigendecomposition of the population matrix takes this particular form, where V is the vector of eigenvectors, and V is the matrix of eigenvectors, and D is the diagonal matrix containing all the eigenvalues. Now, one note here is that under this low rank model, we assume it is possible to have self loops. Right? In other words, we assume it is possible that you have non-zero entries in the diagonal of A. However, in practice, most of the real networks don't have self loops, but the diagonal term contributes very little in comparison to the noise term we are analyzing. So we can actually show that this doesn't make a difference to our conclusions in the end. So most of the theoretical analysis in the network literature proceeds by noting you can decompose A as the signal plus noise form, where signal is the population form of A, and then you just try to bound the noise in some way.
Excuse me?
Yeah.
Can I ask a question?
Please. Yeah, please.
So here then the A will be random and you will introduce the randomness later, I guess, yes?
The A is random. So given, yes, I should be more clear with this. So given the expected value of A, you generate A using independent Bernoulli.
Could you comment on the difference between rank of expectation versus expectation of the rank? Which one is more meaningful in practice?
Which one? Yeah, so this is saying that I believe if I say the population A has rank K, then I believe there's only, say, in terms of communities, there's exactly K communities, and there are exactly K types of rows in my A, K types of different connection patterns. And in what I observe is the random version of the population, then I generate noise on top of the population by sampling from a Bernoulli.
So what I'm thinking is the original A is either 1 or 0. And then you talk about the rank, it makes perfect sense. But if there's some randomness, you take expectation, most probably the components of the A are between 0 and 1 now, yes? Then it's possible it become full rank, yes? While for each A, maybe the rank is very low. But after taking expectation, because it's averaged, it could increase the rank, yes? So I'm just wondering, E of rank versus rank of E, which one makes more sense?
I think I understand where you're coming from, but in this part of the literature, at least, we assume there's always some underlying structure in the population case. Right? The population case is the probability. You have a matrix of probabilities, the probability of edges. You assume there's some underlying structure in this matrix of probabilities, and when you the 0, 1 you observe actually, the structured population probability matrix plus noise. So what you get to observe in the real world is actually not that clean, but the underlying population has exactly K ranks.
Okay, so then for that signal E of A, is it also 0, 1? The component?
The signal of the, sorry, what do you mean by the signal?
So the expectation of A.
The expectation of A is not 0, 1. It's a probability lying between 0 and 1.
Okay. Thank you.
But this is assuming that in the population case, the underlying, if I get to observe the underlying probabilities, then the probabilities have this spectral structure to them.
Okay, thank you.
Thank you for the question. Yeah, feel free to interrupt me at any time. So the case for B is different. Right? So B, remember, B has this particular form. So it turns out the signal term in B is neither the expected value of B nor the expected value of the individual matrices. And a hand-wavy way of explaining this is that if you look at this term, for example, there's an S squared term. And remembering that S is a diagonal matrix with Bernoulli random variables, and squaring the Bernoulli, you still get a Bernoulli. However, when you square the expected value of S, you get probability square. So we're always interested in sparse networks in this kind of setting, so P is going to 0. So the expected value of S squared is much smaller than the square of S. So the signal term in this case for B turns out to be random itself. So we are only taking expected value of A here, and S is left alone. And we can actually show that the signal term, this is the signal term of the matrix B, in the sense that if you look at the spectral norm of the difference, which is the noise, this is much smaller than the smallest singular value of BE. So this BE is now the key term we analyze. So first, this is the result we have regarding the form of eigenvalues and eigenvectors of BE. So we'll need the assumption that VTSV and I minus VTSV, these two matrices are invertible. Then under this assumption, we are going to make up an H matrix with X here is a scalar, Right? So this H matrix depends on the population quantities V and D. It also depends on the random quantity, the S, the diagonal term. And then if we make up this matrix and this determinant equation, set it to 0, it turns out we can show this determinant equation has exactly 2k real non-zero solutions. So now we just index them from -k to -1, and then from 1 to k in this increasing order. So this is my construction of xi. So now let Q1i be an eigenvector of hxi corresponding to the 0 eigenvalue. So hxi is now a matrix, and I look at an eigenvalue of this particular matrix corresponding to the 0 eigenvalue. That's my Q1i. And Q2i will be constructed together using xi and Q1i. And the Q1i and Q2i are both k-dimensional vectors. Now, having constructed these two, I can make up my final Q. My final Q has two parts. Right? The first part related to Q1i, and the second part related to Q2i. And also, we observe that the way we have constructed it, the first part collects contribution from neighbors of individual one, and the second part collects contributions from the non-neighbors from individual one. Right? That's coming from the I minus term here. Then it turns out after this complicated construction, we have exactly the eigenvalues and eigenvectors of the BE matrix. So it turns out this construction gives us the xi inverse. Xi inverse is an eigenvalue of BE, and Qi is an eigenvector of BE. And the converse also holds. In other words, if here Q0 and X0 inverse are the eigenvector and eigenvalues of BE respectively, then the Q0 inverse satisfies this determinant equation we were looking at earlier. And also Q0 can be decomposed into the two parts we were talking about earlier, with the first part coming from the neighbors and the second part coming from the non-neighbors. And Q10 is an eigenvector of H x0 corresponding to the zero eigenvalue. So this construction, or the form of the eigenvalue and the form of the eigenvector, is an if and only if relationship. And we can also show that the rank of BE matrix is exactly 2k. So given this, now we can form the matrix of eigenvectors, the big Q, which is the collection of all the Qi's vectors, right? So the matrix Q is a n by 2k matrix, and it represents all the eigenvectors of BE. And Q can be written as the sum of two parts, the first part coming from the neighbors of individual one, and the second part coming from the non-neighbors of individual one. And we can also show that the orthogonality holds. We can pick the Qi's in such a way to ensure we have orthogonality between the eigenvectors. Now, let me talk a little bit more about the form of the eigenvalues, which will play a role in spectral clustering. Now, let Pn be the maximum edge probability in the whole matrix. And we also assume the first row of A behaves like Pn. So we can think of Pn as essentially the edge density, right? It's the edge density around individual one. And we will assume that it's dense enough that it's bigger than log n over n, and it's also bounded above in some way. Now, with some mild conditions on the D and V, right? These are the population quantities from the population A. With high probability, we can show the eigenvalues of BE behaves like n times Pn to the 3/2. So it is of this order. Now, with a little bit more work, we can show the eigenvalues actually take this particular form. Now, this lengthy matrix is just coming from the H matrix I showed you earlier. It's the main matrix term in that H matrix, the determinant equation we were analyzing before. Now, for the purpose of spectral clustering, we only need to know the order of the eigenvalue. However, this particular form of the eigenvalue gives us one more insight. So looking at this equation, we realize that the minimum eigenvalue of this VTSV determines the gap between the smallest eigenvalue and 0 of the signal matrix BE. And we know that the gap between the smallest eigenvalue and 0 determines how easy it is to do your spectral clustering. So in some sense, this tells you this is a measure of signal strength in your BE matrix.
Excuse me, could you explain intuitively what it means? That condition minimum J P A1J equal to 1 is
yeah, sure. So this is saying the first row of A, which is the neighbors, all the neighbors of individual 1 need to have this connectivity. So it's the density of edges around individual 1.
So that means that the individual is, relatively speaking, very popular, yes?
Yeah, it needs to have, yes, so it needs to have enough number of neighbors, although Pn in general is going to 0, but it can't go to 0 at a rate too fast. So we need a way of controlling what is the minimum Pn, what is the minimum probability of edges around the neighbors of individual 1.
Okay, so that similar means that the quotient is bounded, yes, independent of n. Is that right?
The quotient, sorry, which quotient?
No, the ratio.
The ratio of
the minimum divided by Pn is bounded. Yes, that's what it means. Yes.
The minimum of this term divided by Pn. Yes.
Okay.
Yes.
Okay. Thank you.
Yep. So yeah, so it turns out the minimum, the form of the eigenvalue tells us that the minimum eigenvalue of this term here determines the gap, determines how easy it is to do spectral clustering later. So just a quick summary of what the spectral properties I have shown you so far tells us. So first, we have now constructed the form of the eigenvectors of the BE matrix, the main signal matrix, and it has two parts, right, the neighbor part and the non-neighbor part. We have also derived the order of the eigenvalues, and it's of this particular order. And finally, let's call the minimum eigenvalue of this quantity lambda mean. This lambda mean determines the signal strength you have in the main signal term BE. And because it influences it influences the performance of spectral clustering later, in other words, it tells us how well you can do in terms of community detection using the partial network around individual 1. Or put it in another way, it tells us how important or how central individual 1 is in terms of telling the global community memberships of everyone. So in this sense, lambda mean provides a centrality measure for the node. And naturally, we can show that this quantity lambda mean naturally lies between 0 and 1. And empirically, we can estimate it using the observed version of V from the observed matrix A, because we don't know the population version. And we can also draw connections between this new centrality measure and some of the well-known centrality measures in the literature, which is the degree centrality, which is counting how many neighbors you have, and the eigenvector centrality. We are looking at the influence of your neighbors you're connected to. So under k equals 1, the special case, we can show lambda mean is a mix of the two. It's related to both centrality measures. So now let me move on to talking about actual community detection on the more concrete models. So we first look at the classic stochastic block model, which is one of the simplest models that contains a community structure for all the nodes. Under the SBM, the expected value, the population version of A has this particular form. So it's the pi matrix times P times pi transpose, where P is a K by K connectivity matrix telling you the connections between communities, and pi is the M by K membership matrix. Right. So here we have exactly k communities, and each node is assigned to exactly one of the k communities. So every row in the pi matrix pi I is a member is an element of this collection of standard basis vector from 1 to k. So I pick a community label from 1 to k for every individual I, and then generate then generate my probability of connection, and then generate my observed edges. So in this model, if you have individual I belonging to community K and individual J belonging to community L, then we have the probability of an edge between I and J, and is now you take the KL's entry from the K by K connectivity P. Right? So it's exactly equal to PKL. So the idea is we can write, it's easy to write the SBM, the block model, as an example or special case of the low rank model we were talking about earlier. So all the spectral properties we have derived for BE will carry across to SBM. And we can show that there are actually two types of rows in Q with high probability. And so if we get to observe Q, we just need to cluster the rows of Q, and that will give us the desired answer. But we don't get to observe Q, we only get to observe the empirical version of Q, which is W. Now W is the matrix of eigenvectors of the observed B matrix. Right? And remember, Q is the matrix of eigenvectors of BE, the signal from. So provided Q and W are close enough, we can just do clustering on the rows of W instead, and it should also give us the correct answer in the end. So that is the rough idea behind all spectral clustering techniques. Now recall Pn is the maximum of a connection probability over the whole matrix. And we also need some regularity conditions, right? The first one is similar to what I showed earlier here. Now, without loss of generality, we are assuming individual 1 always belongs to community 1. So this is a condition similar to what I showed before. We also need some constraints saying that almost. So this one is saying the community sizes are almost balanced. Everything is of order n. And this one is saying the minimum eigenvalue of P needs to be bounded below by Pn. So just think of Pn as the edge density. And we also need a lower bound on the edge density. So under this condition, we can show that now if we look at the different rows in Qi, there are 3 cases. If node I and J, they have different memberships, different community memberships to start with, then the ith row in Q and the jth row in Q, the distance between them is bounded from below. Right, that's case 1. Now, if I and J have the same community labels, but the A1I and A1J values are different, so in other words, one of them is a neighbor and the other one is not a neighbor, then the corresponding rows in Q are also different and the distance is bounded below. So there's enough separation between these two cases. And finally, only if you have the same community membership, same community label, and you are both a neighbor of 1, or neither of you is a neighbor of 1, then the rows in the corresponding rows in Q agree. So overall, there are 2k types of rows in Q. So this then our main algorithm goes as follows. So what we showed earlier suggests that we should treat the neighbors and non-neighbors separately. And because we don't get to see Q, we only get to see W, right, from the observed B. So now we apply k-means clustering to the neighbors and to the non-neighbors separately. And this will give us 2k clusters, right, k clusters for each side. Now, this algorithm returns 2 sets of clusters. The final step is to merge these 2 clusters into k communities overall. Now, we can't just merge the clusters by matching the labels, because clusters are only identifiable up to label permutation, right? Whether I call cluster 1 number 1 or number 2, I always have the same grouping of nodes. So it's only identifiable up to label permutation. The idea is now, given these two groupings of nodes, I can construct two estimates of the connectivity matrix P. Right? P here is the K by K connectivity matrix. And the first estimate is coming from this square matrix with rows and columns both being neighbors of 1. Right? That's why the superscript S, comma S. And I construct this estimate by simply doing a count. Right? I count the proportion of edges within each block, and that will give me an estimate of P. And similarly, I can construct a second estimate of P by looking at a rectangular matrix, and the rows are the neighbors of 1, and the columns are the non-neighbors of 1. And similarly, I just do a frequency count and construct the estimates within each block. Now, because I minus S, the non-neighbors clusters can contain a label permutation compared to the grouping I have for the neighbors. And the goal is to find the best permutation such that these two estimates match. Right, so we can just calculate the difference between two estimates and find the best permutation that matches the two. So that is the rough idea behind the label merging, the cluster merging. After having identified the best permutation, now we can merge the two clusters into exactly K communities. And in the end, we have this theoretical guarantee for our clustering algorithm. So we do need some additional separation condition on the K by K matrix P. This is because the two estimates I was constructing before will have additional noise, and I need some concentration property to control the noise, and the signal amount of signal in P needs to overwhelm the noise. So basically, I need the different terms in P to be separated by order Pn, and that's it. That would be enough. And I need a lower bound on the density Pn. Then, with high probability, we can show the proportion of misclustered nodes coming from this algorithm has this error rate, and this rate is going to 0 given this lower bound on Pn. So our algorithm is weakly consistent, or some other people call it, or it has an almost exact recovery property. Now, we can extend everything we have done so far for SBM to the degree corrected version. And the reason we want to include degree correction is that the SBM model is pretty restrictive in the sense that, or in many aspects, but one aspect it doesn't capture, and it's something that we observe often in real networks is the presence of hubs. Right? Some nodes tend to have more degrees, higher degrees than the others. And one way to account for this is to include some degree correction, as in the DCSBM model. So now we introduce a set of degree parameters, right? N degree parameters, each one associated with every node, and construct this diagonal matrix. Now, given the value of your degree parameters, your population A now takes this particular form. So we have the diagonal matrix multiplied to the beginning and to the end. And this changes our edge probability by these two terms here. So to get the edge probability between node individual I and the individual j, provided I know the degree parameter, now the edge probability becomes theta I times theta j times the original connectivity probability as determined by the community membership. So for ease of modeling, we also assume there's a prior distribution, a general prior distribution on theta I, and we assume that theta I generated ID from some distribution with expected value behaving like a constant. So it turns out under this setting, all the theory and algorithm extends nicely to the degree corrected setting, but we do need to make some changes to the algorithm to account for the degree heterogeneity. Right? So as before, we first separate the nodes according to whether they are neighbors of individual 1 or not into 2 groups. Then we apply the spherical k-means algorithm, spherical k-median algorithm instead of k-means algorithm to do the clustering. Right, so this is the objective function for the spherical k-median algorithm, which was first used in the Lei and Ronaldo paper to analyze the original DCSBM setting with the full network. So it's spherical because we are first normalizing every row in W by its L2 norm. And then the algorithm tries to return centroids, k-centroids, these xi's, by minimizing this distance here. Right, so if you first take the L2 norm and then sum up the L2 norm over all the i's. So that's the first change. And the second change, we also need to make some changes to the how we merge the two 2K clusters at the, under the degree corrected block model. And this is because if you remember when we're constructing the estimates for P, we are simply just doing the edge counts. We're counting the proportion of edges within each block. Now with the degree parameters in, these proportions will also contain a component related to the average degree, or the average degree parameter within each block. So that needs to be accounted for by some other function we have defined in the paper, and I probably don't have time to show the detail here. But the idea is that you account for these differences in degree parameters by doing a division, and then you, after doing the division, you try to match the 2 matrices again. So the overall idea is still similar. And the theory also extends nicely to the degree corrected version. We can again show some weakly consistent result for the degree corrected model. Now, with all this, there's still one question we would like to answer. Ideally, we want the clustering error bound to reflect the neighborhood features of node 1. Right? And that will tell me, how differences in the neighborhood feature of different nodes will translate into their knowledge about the global community membership. So in order to do this, we will develop a conditioning argument. We will actually condition on the neighborhood S of individual 1. And to further illustrate our point, we consider a special case where the degree parameters are now generated from a 2-component mixture model. So it's a 2-component mixture model with proportion y, and mu2 is the mean of the CDF F2, the distribution F2. Mu1 is the distribution of F1, and we assume that mu1 is smaller than mu2, meaning that F2 is the distribution that describe the set of the degree parameter distribution from the hub nodes. It's likely to have more degrees than the rest of the nodes, and F1 describes the distribution from the non-hub nodes. So this is the setup, and then we need one more notation here. So NJK counts the number of nodes who are neighbors of node 1, and they lie in community K, and their corresponding degree parameter is generated from Fj. So it just counts the number. So I look at all the neighbors of individual 1 and divide them according to their community membership and which Fj they're generated from. So under this setting, we have this conditional result, which is that provided you have some lower bound on the edge density again, then conditioned on the neighborhood and conditioned on the degree parameters, with high probability, we can show the proportion of misclustered nodes now depends explicitly on the neighborhood features of an individual 1. Right, so this is the key term here. We can see that as this term increases, then you have a smaller upper bound on the misclustered nodes. So looking at this term more closely, it is saying that if individual one, first of all, if individual one has more neighbors, then I have a smaller bound on the misclustered nodes. Or if my neighbors, the number of neighbors or the degree of individual one is fixed, then a higher proportion of these N2Ks, and remember N2K counts the number of neighbors generated with degree parameters generated from the hub distribution, the higher proportion of N2K is going to make this upper bound smaller also. So in other words, this is saying knowing more powerful neighbors across all communities will help individual one identify the global community membership. And coming back to the centrality measure, we mentioned earlier, the lambda mean, we can actually show the lambda mean behaves like this ratio here. So the same interpretation applies to the centrality measure. The more powerful neighbors you know, the better you're going to perform. So finally, let me show some numerical results. So here we're just first generating a simple 2-block SBM with this particular connectivity pattern. So Q is, you can think of Q as the edge density, and we vary Q from a fixed number to all these quantities depending on N, and N is varying between 300 and 2,100. So in this table, we are showing the fraction of edges observed by individual one. So you can see the fraction of edges observed varies between 10%, roughly 10% to 50%. And here we are plotting the clustering error if we apply our algorithm. So we can see that for most of the Q choices, it eventually converges to, the error converges to 0 as N increases. But for this line here, which is Q density equals 1 over square root of N, it doesn't seem to converge. So this should be, this is beyond the parameter recovery regime our algorithm is capable of achieving. And corresponding example under the degree corrected version, same P, same K, I'm just generating the degree parameters as IID uniform distribution. And we can see here the trends are very similar, except the convergence rate is slower for most of the Qs. And finally, I want to show some result related to the mixture case. So now I'm generating the degree parameters as IID mixtures from F1 and F2. So F2 has a higher mean, representing the hub nodes, and with proportions with these two proportions. So now I'm just generating one instance of the adjacency matrix A, and I apply my partial clustering algorithm to every individual in the network. So what I want to compare here is how the clustering accuracy for each individual, how it correlates with different kinds of centrality measures. So I'm looking at the degree centrality, the fraction of edges, the eigenvector centrality, and the betweenness centrality. The betweenness centrality counts the number of shortest paths through a particular node. And the last row is the empirical version of lambda mean, the eigengap centrality we proposed earlier. So we can see that both under Pearson correlation, whether you do it by Pearson correlation or Spearman correlation, the lambda mean has the best correlation with the clustering accuracy. And more interestingly, if I compute the correlations between these different centrality measures, we can see that for this simple synthetic network, at least, most of the other 4 types of centrality measures are highly correlated, with correlation above almost close to 1. But the lambda mean is something different. It has lower correlation compared to the others, suggesting that it might have captured a different aspect of the information, of the network information. So let me talk a little bit about 2 sets of real data. And the first one is the well-known karate club example. And so each node here represents a member in the karate club. And it is known that the node A and the node H here are two hubs representing the instructor and the administrator. And the members split into two communities after some dispute between node A and node H. So here in the table, I'm showing the degrees of each node. For these 6 nodes we have selected for comparison, the fraction of edges they observe within their partial network, and the clustering, the community detection accuracy using that individual as the center. So quite surprisingly, these 2 hub nodes don't give you the best clustering accuracy. Instead, this node 20, which only has 3 edges, gives you does an almost perfect job in telling the global community membership. And a closer inspection on the connection around node 20, we see that it's connected to both A and H, which sort of coincides with our earlier theoretical analysis that if you are connected to powerful neighbors, then you have better information about the global community structure. And finally, this data set is about the introduction of a microfinance program in Indian villages, and has a very rich structure with independent sets of networks, social networks, and node covariates, and microfinance program participation rate, and so on. So the original goal of the paper is to model the spread of information about a particular microfinance program in Indian villages. And for each of these villages, we have a social network. And this time the nodes represent households, and each edge is an undirected or binary representing any of the 12 relationships collected in their survey. So these relationships can be borrowing or lending of money or material goods. And for community labels, we used the caste information available in their survey. And each village also has a few predefined leaders serving as injection points for the information. So what happened was they first held meetings with these leaders within each village, tell them about this program, and then asked them to spread information about this program. So we analyzed 39 villages, and because these villages are far apart enough, they can be viewed as independent copies. They can be viewed as independent social networks. And the number of households varies between 24 and over 100, and K between 2 and 4. So the first question we want to ask is that, do these predefined leaders have better information about global community membership than the non-leaders? So within each village, we compute the average clustering accuracy for the leader group and the non-leader group and plot them in this scatter plot. So points lying above the diagonal line is saying the leader average is better than non-leader average. And we can see that in most cases, that is indeed true, which to some extent justify the choice of these leaders in the villages. And next, we also again, we look at the correlation between the centrality measures and the clustering accuracy. So we did this computation for every village, and within each village, we take the average across the leader group and the non-leader group, and we computed the correlation using Pearson correlation and Spearman correlation. So these are all the combinations in the plot. So we can see that overall, our eigengap centrality, the lambda min hat, has the most stable performance under all these combinations. The between centrality did pretty well for one of the combinations, but not so well for the others. And finally, we want to check whether in addition to picking up information about global community structure, does this lambda min as a centrality measure include additional information beyond community structure? So we looked at the program participation rate as a function of 2 centrality measures. The first one is our centrality measure, and the second one is the diffusion centrality measure, originally proposed in the paper to capture exactly this information, this program participation rate. So we can see that actually it turns out the program participation rate is correlated to our centrality measure. even with the slightly significant p-value, the dependence is the significance level is not as big as the diffusion centrality measure, which is originally designed to capture this information, but still it shows us that our centrality measure is useful for something beyond just knowing global community memberships. So let me sum up what we have done. So we have introduced an individual-centered partial information network to study social networks. And in order to do global community detection, we first derived the theoretical properties about the main signal term in the partial adjacency matrix. Then we showed how we can develop consistent community detection algorithms under 2 concrete models. And as a byproduct of our analysis, we also propose a new centrality measure based on the eigengap. Now, this framework by itself gives us a lot of possibilities for future work. So first thing is that instead of considering everyone's community membership in the whole network, maybe I'll only care about individuals within or reached by my partial network, right? But this one is going to be, in the paper, we have some empirical results showing our clustering algorithm can still be applied to this case, but the theoretical analysis of this is going to be harder because the number of individuals in this case will be random, adding another layer of complexity to the analysis. So we're going to leave it for future work. Now we can also consider the mixed membership block model. On top of degree correction, we can consider the case L equals 3. We haven't really talked about how to select K. We assume K is always known in the current analysis. And we can also try to introduce some noise in my second layer of edges. Maybe I'm not so confident about the connections between my neighbors and their neighbors. And we can also try to combine information from multiple individual partial information networks. And the list goes on. So with that, I would like to thank my collaborators again, Dr. Xiao Han and Dr. Xin Tong in the Marshall Business School. And we would also like to thank Dr. Yijing Xin for his discussion, many helpful discussions on the microfinance data. So thank you for coming to my talk, and I'll be very happy to take any questions. Sorry, I went a bit over time.